This is the 6th lecture in multivariate linear models. So we have introduced the multivariate linear model. That was in notation, it was y is equal to xb plus e. Let us remember the univariate setup, y is equal to x beta plus epsilon. So it is the multivariate analog, and this X matrix is of size n cross p. It has rank R. The matrix B has p cross d size, and the rows of the matrix E, which is the now multivariate analog of the epsilon vector in univariate linear model, that has their IID independent identical distributed multivariate normal distribution in d dimension with mean vector 0 and dispersion matrix sigma. We have already talked about estimation of the beta matrix, B matrix, and also the sigma matrix. That was the least square. We have talked least square estimate, discussed least square estimation. Then we went on to discussing least square estimation of B subject to AB is equal to 0, then AB is equal to C, where the system AB is equal to C is a consistent system. Now we are going to develop a test for the hypothesis AB is equal to C. What we shall do, we shall derive the likelihood ratio test, the functional form. We shall state the null distribution with little bit of technical background, and in the process we shall state some more distribution theoretic facts. So this is the 6th lecture on multivariate linear models. Let's state the model again. This is y is equal to xp plus e, and x is of size n cross p with rank R, and this includes both regression scenario and also the standard ANOVA models when the x need not be of full column rank. B, the matrix of parameters is of size p cross t. Rows of the matrix E, they are independent and identically distributed normal variables with mean 0 and dispersion matrix sigma. We have already discussed estimation of this B matrix, least square estimation without any restriction, and also under the restriction AB is equal to 0 initially and then AB is equal to C, when AB is equal to C is assumed to be a consistent system. Now in this lecture we wish to develop a test for AB is equal to C, where A is a Q cross P matrix of full row rank and AB is equal to C is a consistent system. And since X is not typically assumed to be a full column rank matrix, that means R is likely to be less than P, then we assume A is equal to mx. Let us remember that such an assumption ensures estimability of this quantity AB. Then only we can go for estimation of this quantity AB. So we assume that A is equal to mx, where M is a Q cross N matrix of rank U. So that's that's the assumption we make, and what we shall do, we shall derive the form of the likelihood ratio test statistic and also the null distribution, and also state some distribution theoretic facts in the process. So let's see the assumption carefully again. So this is the multivariate linear model, y is equal to xp plus e. If we write the columns as y superscript 1, y superscript 2 up to y superscript d, and the rows by y1 transpose up to yn transpose. So what are these objects yi transpose? These are the vector of observations on d response variables for the ith sampling unit. Initially, earlier in the univariate linear model, we had d is equal to 1. So there is only one response variable that we have to measure. Now we have d response variables. So therefore, if we look at the columns now, and if we restrict attention only to the first column, what we shall get, in the first column consisting of n independent measurements on the first response variable for n sampling units. So if we go across for a fixed column, if we go along the rows, then we shall get n IID measurements on the corresponding response variable. And for a fixed row, if we proceed along the columns, those are for the ith observation, ith sampling unit, those are the d response variables that we have data on. And let us now write B is equal to beta 1 through beta d in superscript. The rows of capital E matrix, they are denoted by epsilon 1 transpose up to epsilon n transpose. Then from y is equal to xb plus e, we get this B transpose xi. Just notice that this is exactly the same kind of linear model that we have seen in univariate linear model. So yi is equal to b transpose xi plus epsilon I, and y superscript j is equal to x beta j plus epsilon j from 1 through d. And the assumption about A is that the rows of E, that is epsilon 1 to epsilon n, are IID multivariate normal variables, normal d 0 sigma. Alright, so this is it. And we denote the rows of capital A matrix by AI transpose. And we assume that the constraints AI transpose beta j must be estimable. The assumption that we were talking about. Otherwise, if it is not estimable, we cannot even go for a testing problem, settling a testing problem. In other words, we assume that following the univariate scenario, essentially the same kind of arguments will imply that A is equal to mx for some q cross n matrix M. And from q is equal to rank A, it follows that rank of M is equal to q. That's one can prove it. So what is our agenda now? Our agenda is to test for this hypothesis. AB is equal to C. It is assumed to be a consistent system 1, and the capital A matrix is of the form M times X, where M is some q cross M matrix and rank is q. This can be proved. We are not making this assumption. From this representation, A is equal to mx, and the fact that rank of A is equal to q, that is the rows of A is a full row rank matrix, we can show that rank of M is equal to q. It's not a hard, difficult proof. We have seen it in one of our earlier slides. So what we do now, we assume that the jth column of capital C is Cj. We denote by C superscript j. So what are the corresponding hypotheses? If we just look at this AB is equal to C, and we recall that the columns of B are denoted by beta 1 through beta d, then this is basically this hypothesis AB is equal to C means A beta 1 is equal to C1, A beta 2 is equal to C2, up to A beta d is equal to CD. So therefore this hypothesis can be written as intersection of all this. So H0j intersection of j from 1 through d, this is same as AB is equal to C. Now why this is at all being done? Let us remember that in the case of univariate linear model, we have seen how to test this hypothesis. Basically, you assume that this is estimable first of all, then you estimate beta j by least square estimate, and then you look at the A post multiply by the corresponding least square estimate of beta j. From that you subtract Cj and you do the standard analysis where you have to also use the estimate of the dispersion of this mean square error of this. Now once we did this, we have also seen that this testing hypothesis problem, for that one can show technically that the test statistic turns out to be a difference of two residual sum of squares. Under the residual sum of squares being computed under the null hypothesis and without any restriction over the beta parameter, and it's a principle, and we are going to use basically the same thing. So our test procedure will be based on the same principle. So let us recall the following. The development of the test procedure is in successive steps. This is one of the things that we should remember. And our unrestricted least square estimator of B, denoted by this, satisfies the following: theta hat. Theta hat is equal to x b hat is equal to pxy. What is pxy? Px is the projection matrix onto column space of X, and the least squares estimator of B, subject to AB is equal to C, assumed to be a consistent system, denoted by B hat H, satisfies the following: x bh hat is equal to x b hat minus etc. And this x bh hat we denote by theta h hat. Basically this is the xb, the mean of y, estimate of that under the restriction AB is equal to C, and this is without any restriction over B. Now we remember that, we also remember now that once we have got hold of this, these are basically the fitted values. If we remember x beta hat etc., those are the fitted values. This is the fitted value of y without any restriction of B, that is the standard list. You simply find out the standard least square estimate, plug in here and get the fitted value, and here you do the same thing but on the additional restriction that AB is equal to C. Then you compare the fitted value. Now if we subtract the fitted value, the two different set of fitted values under the restriction and without restriction, what we shall get? We shall get two different set of residual sum of squares. Now if the model is our H0 holds, then we expect that the fitted values also coincide. So therefore, the large values of the residual difference between residual sum of square, rather large value of difference between these two fitted value, that's an indication that perhaps H0 is false. That's the principle, and we borrow the same principle. And based upon that principle, what we do, we introduce these two matrices, EH and ES. What is ES? E is the residual sum of square matrix. Earlier we had residual sum of square, now we have residual sum of square matrix. It is defined as y minus xb hat transpose y minus xb hat. That was exactly the same, that is exactly same as the earlier definition in univariate linear model. What we talked about, replace this b hat by beta hat. Similarly, we look at EH. This is the error sum of square under the null hypothesis. So this is y minus xbh hat transpose y minus xbh hat. And we remembered that if these two are close to each other, then we say that we don't have much evidence in our data to reject H0. And what are the underlying technical results? Technical results are, when H0 is AB is equal to C is true, then this matrix ES and EH minus ES, they are independently distributed as this Wishart distribution in dimension D, degrees of freedom n minus r, it is sigma, and Wishart distribution Q and sigma. What is Q? Q is the rank of A. A proof of this result is available in SEVER, which we are heavily following and dependent on in this series of lectures. And we should notice in this connection that it is this result is very similar to the result where relevant sum of squares in usual univariate linear model are independently distributed, each having a chi-square distribution under null. So that's the, I should say that is a very basic result, and we are essentially extending that basic result when we are dealing with multivariate linear model. We have a nice theory for multivariate normal distribution, we have nice theory for projection matrix, and everything goes through nicely. All right. So what we do, we introduce this matrix EH minus ES. Let's remember again that difference between these two we have to somehow quantify. So that's what we difference is called EH minus ES. And let's see that there is a nice simplification of this EH minus ES. AB hat minus C, then post multiplied by A x transpose x inverse A transpose inverse A beta hat minus C. We have seen an exactly same thing in univariate linear model, which is lambda transpose B minus D transpose, lambda transpose, etc. And what did we do? We notice that this is basically the difference between, it should be lambda transpose beta hat. Lambda transpose beta hat, this is essentially the deviation between lambda transpose beta hat and D. So if this deviation is large, those large values are indeed significant. It is in exactly the same manner, if this is large in some sense, then we can declare that perhaps there is evidence in the data that H0 is false. So this is essentially the same thing what we have done earlier, except that now we are working with matrices. So what is the likelihood ratio test statistic for this? So for likelihood ratio test statistic, under the normality assumption, we have to write down the likelihood, which we did not do here. It turned out that this likelihood ratio, which is denoted by this script L, etc., capital L theta h hat. What is theta h hat? We have seen earlier. It is this object, x bh hat. What is sigma h hat? It is the corresponding error sum of square matrix divided by n. And in the denominator, L theta hat, what is theta hat? This x beta b hat, and sigma hat is error sum of square matrix divided by n without any restriction on beta. So once we notice this representation of this likelihood ratio test statistic L, one can without too much of technical work show that this quantity L, it is same as determinant of sigma h hat whole to the power minus n by 2 divided by determinant of sigma hat whole to the power minus n by 2. This is not enough, not at all a difficult technical exercise. And then we look at this, what is this likelihood ratio test statistic or equivalent? It is lambda L to the power 2 by n. It turns out that this quantity capital lambda is same as determinant of ES ES divided by determinant of ES plus H. We have already talked about what is ES. ES is the error sum of square matrix without obtained through estimation of B without any restriction. Then there is something called EH, that is the error sum of square matrix obtained through estimation of B under the restriction A B is equal to C, and this is the deviation between EH and ES. And it turns out finally that this statistic has a Wilks under null distribution is Wilks lambda under parameters D, N minus R and Q. So this is a new distribution that Wilks introduced in this connection in the context of multivariate analysis long back, and we see that everything falls in very nicely in the all that we wish to point out that as in univariate linear model here the two aspects, one is the normal distribution, the other part is the work with projection matrices. They play a very crucial role. So that's what we have obtained. Therefore, in this case, we have so far talked about in multivariate linear model estimation of B without restriction. Then under the restriction AB is equal to 0, AB is equal to C. AB is equal to C we did not discuss much because it is minor additional work from AB is equal to 0. And now we have finally come to a stage where we can go for testing AB is equal to C. And these are the final result. This is the likelihood ratio test statistic or this one, and it has a null distribution Wilks lambda. Thank you. So let us now briefly tell about what we have done in this lecture. As before, we have been continuing the discussion on multivariate linear models. The model is y is equal to xb plus e, where x is the design matrix, b is the matrix of parameters, e is the matrix of errors. And let us remember that it is very much similar to the univariate linear model y is equal to x beta plus epsilon. In this case, x is of size n cross p, it has rank r. And B is a P cross D matrix, and the rows of the capital E matrix, they are independent, identically distributed, d-dimensional normal variable with mean vector 0 and dispersion matrix sigma. What we have done in this lecture, we have developed a test for AB is equal to C, where there is a linear restriction on the parameters in B. We have already talked about, not in this lecture but in early lectures, estimation of least square estimation of B. Then least square estimation of B is subject to AB is equal to 0, then subject to AB is equal to C, where AB is equal to C assumed to be a consistent system. What we have done in this lecture, we have derived the form of the functional form of the likelihood ratio test statistic for the testing problem H0 AB is equal to C, and have obtained an equivalent expression of in terms of relevant error sum of square matrices of the likelihood ratio test statistic. Then we have talked about stated the null distribution. The null distribution turned out to be Wilks lambda with appropriate parameters. This is a new thing. And in the process, we have learnt a few distribution theoretic facts.